the audience. Haled, thank you very much.
All right. Before I begin, I just want to thank everyone for being here today and listening to these presentations. And of course, I want to thank my project sponsor, Askala, for all his help with this project. With that being said, I'm Nick Vinansky, and today I'll be presenting to you the topic of my capstone research, which is entitled Volt-VAR Control, Impact and Benefit Analysis. To begin, I'd like to present a brief outline of what I'll be discussing today. So I will be starting with background on the project, exactly what Volt-VAR control is, and why I'm doing this analysis. Secondly, I will provide a first semester recap of everything I completed the first semester and how it applies to LVM, savings, and things of that nature. Additionally, I will go into my second semester goals. So what my goals were for the semester include an examination of bellwether data, which is downstream meter data and its impact on LVM plan generation process. And additionally, I would perform a financial analysis on the LVM generation system based on customer rates. From here, I'm going to move into the methodology I used to complete these goals, the results obtained, and the conclusions drawn from the results I obtained. So to begin, my project is sponsored by PPL, specifically by their distribution operations team. And my goal is to perform an impact and benefit analysis of the Volt-VAR control software. So essentially, my goal is to determine how PPL is benefiting operationally as well as financially from the use of this Volt-VAR control software. The software that they use is called Load and Volt-VAR Management, or LVM. And the way that this process works is that SCADA measurements from feeder lines are used to correct power factor and provide voltage regulation throughout the distribution network. Additionally, this is done through the use of three major devices, which are capacitor banks, voltage regulators, and load tap change transformers. Now I'll get into the first semester recap, so everything I completed the first semester. In the first semester, I examined upstream voltages, specifically at the bus level. So I looked at bus voltages at 3 different substations, and using a year's worth of data, I created average bus voltage curves over a 24-hour period. And from here, I calculated the standard deviation in each of the bus curves and determined that the substations that were utilizing LVM for the entirety of the year experienced a much lower standard deviation, as well as a much flatter voltage curve as shown here. And this was indicative that the LVM application was working as intended. So as shown by the results on the right-hand side over here, we see that station 3, which operated under LVM for the whole year, had a standard deviation of 0.03 in the bus curve, as shown here. Station 2, which operated for a portion of the year under LVM, had a standard deviation of 0.07, also very low. And then Station 2 for the months of July and August did not utilize LVM and experienced much higher standard deviations. From here, I'm going to discuss my goals for this semester. So what I wanted to look at was examining bellwether data and its impact on LVM plan generation. So bellwether data is essentially a different algorithm than the LVM algorithm that's used. LVM has the possibility to be paired with AMI, or automated meter infrastructure. And what's done is the bellwether algorithm determines the 5 highest voltages and 5 lowest voltages on the feeders coming from the substation. So that's 10 total points. And then ideally, the LVM algorithm runs 20 seconds after this process occurs and determines exactly which points to consider in its LVM plan generation process. Additionally, I performed a financial analysis of the LVM application from the customer perspective, which resulted in some pretty great results in the hundreds of thousands of dollars. So the methodology used for the first portion of this project, I examined 24 hours worth of data from a Harrisburg substation. Data was collected every 30 minutes over a 24-hour period, meaning I had 48 bellwether files to examine and 48 LVM files to examine. From here, I compared the bellwether recorded data with the LVM plan generation data, and then determined the LVM plan dependence on bellwether data. This is shown in the next slide. So essentially what I did was I used the bellwether files that were accepted. So of the 48 total files, only 25 of the LVM plans were actually accepted. An LVM plan can either be accepted or rejected in the LVM plan validation phase. The plan will be rejected if power factor is not corrected or if there's still voltage problems within the system. So of the 25 accepted LVM plans, I determined that 98% of the time, the bellwether data was considered in the LVM plan generation process. And the way I did this was I matched the load IDs and meter IDs shown here. So this is an example of what the bellwether data would look like. So these are the 5 highest voltages that were recorded on the line for feeder 1, and these are the 5 lowest voltages, which were from feeder 2. From here, I compared the load IDs and meter IDs here with the LVM plan generation and saw that it matched 98% of the time as shown. This 2% that was not matched could be contributed to the system design. So it was originally thought that bellwether data was not really considered in the LVM plan generation process. So it will not necessarily be used all the time in LVM plan generation. From here, I'm going to move on to the methodology used for the financial analysis portion of the project. So I was provided data for the same substation that I was referring to for the date of January 30th, 2020, and the date of March 27th, 2020. The January data was data that involved the LVM process, and the March data did not involve the LVM process. So what I wanted to determine exactly was how the voltage between the 2 days changed over the course of that time period. So what I did was calculate the total instantaneous voltage on each feeder by summing all of the meter readings on the feeder for both of the days. And then I took the difference between the 2 different days to determine the total voltage difference between the 2. From here, I calculated total line impedance and transformer impedance based on specific assumptions that I will get into on the next slide. And then I calculated current using total voltage and impedance. So I took the total voltage from the first step and divided by the total impedance to get total current values for both of the days. I then took the difference in the current for both of the days to calculate the change in power between the 2 specific days. And this was done by multiplying the change in current by the change in voltage. From here, I converted to megawatt hours over a 24-hour period, and then I multiplied by a customer rate of $7.49 per kilowatt hour to obtain financial result. So the assumptions used in these calculations include a feeder length of 10 miles, which was an arbitrary value, a wire material of number 4 copper, the fact that line impedance was based on the wire material determined, and that transformer impedance used was the PPL specified minimum value. So these are the results of the voltage portion that I discussed. As you can see, this is during LVM, this was not during LVM. And these are the change in voltage between the 2 days. So as you see, the voltage on feeder 1 increased by 1,078 volts, feeder 2 increased by 321 volts, and feeder 3 increased by 1,800 volts. Based solely on line impedance, I calculated financial savings for the year for the customers on the line to be $174,000 for feeder 1, $15,000 for feeder 2, and $486,000 for feeder 3. I performed additional calculations as well. This calculation was based solely on transformer impedance, not considering line impedance at all. Using these assumptions, I determined that the financial savings for feeder 1 were $70,000, feeder 2 was $7,000, and feeder 3 was $195,000. Finally, I did one final calculation based on both total transformer impedance and total line impedance and determined financial savings of $50,000, $4,000, and $139,000. So based on these results that we obtained, we saw that the voltage increased along each feeder while not under LVM operation. feeder 3 experienced the greatest change in voltage and thus the greatest financial savings. And the financial savings ranged from thousands of dollars to hundreds of thousands of dollars in each case, no matter the assumptions. In conclusion, the bellwether data is considered heavily in the LVM plan generation process, as shown previously. The voltage along feeders is lower under LVM operation, which was shown in the first semester results, as well as the financial results. The customer does in fact benefit financially from the use of LVM in the units of thousands to hundreds of thousands of dollars. And finally, PPL benefits operationally from LVM as voltage is lower along distribution lines, leading to a longer system life. And with that, I'm going to open up the floor to questions. Thank you.
Thank you, Nick. Questions for Nick Vinansky?
Rudy, can you hear me okay?
Please speak up.
Rudy, it's Al Rutz. Can you hear him? Can you
Yes,
hear
yes, we can hear you. Go ahead, Al.
Nick, couple of questions. I just joined halfway through your presentation. My
Yes.
apologies, but I saw a couple of the assumptions there that I think are pretty far off from reality.
Okay.
It said that you assumed number 4 copper on the lines.
Yeah.
And a line like that leaving a major substation would be far greater than that. It'd probably be 477 or 336 aluminum.
Okay.
And the lines out of that Harrisburg substation are nowhere near 10 miles long. So I just was curious, how much would those data points, how much would those assumptions be skewed if let's say if the feeder was only 5 miles long and the wire size was 5 or 10 times the circular mill of what the assumptions were?
Well, we would get much different results, definitely much less financial savings. We would have greater financial savings in that case because the model was specifically based on line impedance. So with less impedance, you would have greater currents. And based on the model that I used, that would result in greater power change and thus greater financial savings. Does that make sense?
Yeah, I think so. Yeah, I said it was like, I'm not sure, did they not give you actual feeder sizes and lengths that you had to make those kind of assumptions?
The assumptions were made with the help of my project sponsor. So that's how I came up with those assumptions. I didn't necessarily come up with those on my own. We decided that that was the best idea to do.
Okay, and these are all overhead circuits, I'm assuming.
Yes, as far as I know.
Okay, all right, thanks, Nick.
Any other questions for Nick?
Hi, Nick. This is Kim Gautner from PPL. I wasn't your sponsor on this project. My colleagues were, but I very much enjoyed it. To Al's point, the average feeder at PPL is actually 27 miles long. Out of the 1,200 circuits that we have, our average is 27 miles long. So how would that affect the financial calculation?
Well, with the longer the feeder, the greater line impedance that you would have, which would result in a lower current, which would definitely result in lower financial savings. Does that make sense?
Would it be proportional?
Based on the model that I used, I don't believe so. Because, well, actually, yes, it might be proportional because then we would have larger voltage on the line as well. Right?
Your voltage at the bus would remain the same at the substation or similar, but it's an interesting thought process. The other challenge with a really long line, a line as long as 27 miles, some of our lines are as long as 100 miles, that voltage is harder to control as a whole. So that's one of the benefits PPL is at least thinking that LVM might be able to provide is better control on these very long, stringy feeders that the rural areas of Pennsylvania are notorious for. So I think that might be a slightly different calculation, but still a very valuable, this is still very valuable data, and a really solid calculation. So thank you.
Thank you.
Yeah, this is Al again. Kim, when you say a feeder is 27 miles, you have to be assuming like the additive length of each individual single phase, three phase, whatever. Whereas when I look at the length of a line, it's like maybe the longest continuous, not the sum of all the little feeders going off to the side. Is that, it's, when you say 27 miles, you're saying there's 27 miles of conductor on the line, I hope, and not that there's 27 miles from the start to the most distant point.
Right, that's 27 line miles. So that's single phase and three phase combined. It's not each conductor on three phase added together, but it is a three phase line versus a single phase line. Typically, it is not 27 miles from substation to the last customer on the line, or the farthest customer on the line. That's a good point.
Yeah, yeah. Again, I haven't seen Nick's total model, but you know, you can't assume that all that current flows all that distance for 27 miles, for instance.
Right, absolutely.
Okay, thanks.
Anything else from any? Nick, sorry. All right, thank you, Nick. So why don't you unhook your screen and have